Doesn't even feel hot. Hello, thanks for checking out this video where I'm basically going to show you how to make that plasma jet that I just showed you a little clip of at the start. So really what I wanted to do is come up with an interesting kind of project to showcase some of the theories that I've taught in my previous videos. So this is looking at resonance circuits, it's looking at capacitive dividers and things like that. So really what I thought I'd do and what would be a pretty neat thing to try was to see what the highest possible voltage we'll be able to generate from one of those little 9-volt PP3 batteries. So the tiny little ones you buy from the supermarkets, the square, rectangular ones, they give you 9 volts. They last about 10 seconds if you draw a lot of current for them. So they're pretty feeble, but I want to know what's the highest voltage we can get out of those. Certainly it's enough to generate some plasma as I showed you, but maybe we can go even higher. So the plan is really to use widely available components, so stuff I bought from Amazon, and everything you see today everything you'll see in these videos is things I bought from Amazon. So really you can try that yourself at home. I'm not really using any fancy equipment, although I do use an oscilloscope and a signal generator, but they're not really necessary. And, you can try this at home, but really if you do, you must be careful because we can generate some incredibly high voltages. And in later videos, you'll see that we can get up to sort of tens, if not even 100 kilovolts. That's not in today's video though. That's going to be in a few videos time. So really the plan is today, I'm going to go through the design of the circuit, what's going to allow us to be able to generate that plasma. So really the plan is I'm going to take my 9-volt battery, which gives a DC voltage, and design a switch mode power supply. So that's going to be the focus of the video today. That basically chops the DC up into an AC signal. So if my DC is 9 volts, the AC signal is going to go between plus and minus 4.5 volts. That AC signal is enough to drive a transformer. And the transformer I'm going to use is not a normal transformer. It's actually an ignition coil from a car. So it has a very high step-up ratio, but I'm actually going to use it as a resonant transformer. So I'll explain more about that later. And then I'm going to use that to generate the plasma you saw at the start of this video. So in future videos, what I'm going to do is I'm going to take the AC from that high voltage transformer, put it through a voltage multiplier. That's going to give me a very high voltage DC out, sort of maybe, 20, 30 kilovolts. And I'm going to use that to charge up a Marx bank or a Marx generator that generates an extremely high voltage pulse. So there we really will see how high we can get a voltage from a 9-volt battery. That's going to be in a future video. Okay, to start making this circuit, what I'm going to do is I'm actually going to use this Easy EDA schematic editor. The reason I'm doing this is I know it really well, and also that it's really great for making PCBs or printed circuit boards. So in a future video, I'm probably going to make a printed circuit board out of this design. So it's great if it's already in this software because it's really easy to get the boards made. Basically, once you've done the PCB design, it's like 2 clicks and you can get them ordered from China. They're like $3 or $4 for 5 boards. They get delivered to your house, here in the UK, in like 4 to 5 working days. It's expensive, sort of like $20+, but they do come quickly and they are really good quality. So I like to use this JLC PCB. Obviously, I'm not sponsored by them, but loads of people are. And yeah, it's a really good service. You can also order the components from them, and they have like a deal with this LCSC Electronics to deliver the components. So I'm going to get the part numbers from here, and I'm going to use them to draw the circuit diagram. Okay, so first thing I'm going to need, I've made a list of basically the things I need. I'm not so worried about the exact values of what I use here, or even the footprints. I just want to get the right symbols into the circuit diagram so you can understand what the circuit diagram is. And as I'm building the circuit diagram, I'm going to talk through how it works. Okay, so the first thing I'm going to need is a half-bridge driver, HB driver. And the one I've chosen is an IR2153D. No, not D, without the D. More modern chips have a D, but I bought this off Amazon and it doesn't have the D. And that basically means it's missing an internal diode that we'll need to add. Hence the reason my list has a diode written on it. So the other thing I'm going to need is a couple of MOSFETs. I can already see one here on the front page. This one will do nicely. I need an electrolytic capacitor, or maybe a few of them. Aluminium electrolytic leaded. Really, as I already mentioned, the actual value of it is unimportant at the moment. When we actually come to the build the circuits, these obviously will be important. I need a potentiometer. One problem with this is the search is not so good on this website. So it's easier to just go through the website sort of headers. Let me just check if this part is in stock. Oh yeah. Okay. So that's all I'm going to be doing is searching them and then adding them onto the schematic. I need some normal capacitors. So as you can see, I'm pretty much taking the first ones available. And I'm just going to this Easy EDA to make sure they have the package for them. Sometimes it'll say there's nothing available. And you won't be able to place it, but here they're available. So I'm going to need, let me think, 1, 2, a bootstrap capacitor and a timing capacitor. Okay. And the last thing I need is a diode. I'll explain why we need all these things in a moment. See what I mean? I've just searched diode and it's just come up with a load of random weird stuff. Easier to go diodes, fast recovery diode, which doesn't really matter which one. DO15. Grab one of these. And let's place it on the schematic. So as you can see, we've got some components there. Let me just put these ones in. No. We're going to need 2 of those. And what else are we missing? The electrolytic cap. Okay, I think that's all the components. So if we just have a look at the data sheets, we can immediately see something about what we shouldn't be doing. We shouldn't be using this for new designs. We should be using the IRS 2153D. And as I already mentioned a couple of times, that D is important. Basically, if it has a D on it, the package or the IC, you don't need this external diode shown here in sort of typical connections. It's basically embedded within. Oh, well, there you go. So let's have a think about how this works. Ignore this capacitor and this inductor for a moment. Let's just have a look at this. Basically, what's going to happen is this IC generates square waves. It generates two square waves that are out of phase by 180 degrees. So if low out is high, high out must be low, and vice versa. If high out is high, then low out is low. And basically that's going to switch these MOSFETs on alternatively. So for some portion of time, this one will be on, and the voltage at the midpoint will be at 0, and then they'll flip around. So this will switch on, and the voltage at the midpoint will shoot up to the rail voltage as drawn here, maximum 600 volts. We'll be using 9 volts there. Okay, that's basically how it works. And here, RT and CT are basically what control the frequency of that switching. So it's the timing resistor and the timing capacitor. We'll look at the data sheet in a little bit more detail in a minute. We're not going to bother with a shutdown switch, but we will need to include this diode and this capacitor. And basically what these are for is when this MOSFET switches on, the voltage here drops to 0, and then this capacitor charges through that diode. So that will charge up to the charging voltage around maximum 15 volts. In our case, it's going to be 9 volts. And then when the switches flip again, the voltage here is no longer 0. Look, it's not referenced to ground. Basically, if neither switch was on, the voltage here would be 300. And we need this additional 9 volts across this capacitor to be able to switch this gate of this MOSFET on. Okay, so this little arrangement here is called a bootstrap, and it basically provides the voltage needed to turn this MOSFET on, i.e. the 9 volts or the 15 volts between the source of the MOSFET and the gate of the MOSFET when the MOSFET's not referenced to ground. So don't worry about that. That's just how that chip in particular works. You could actually achieve the same thing using a transformer coupling to that gate. But that is this self-oscillating half-bridge driver, and I find it absolutely bizarre that in the datasheet they don't show the other half of the half-bridge. This arrangement here is very odd. Okay, so we can see basically how it's wired up. We've got 8 pins, VCC common, and we've already spoke about the timing components. We've talked about the bootstrap, and we've talked about the high out and the low outs. Other important information in this datasheet. Let me scroll down, because it needs 5 milliamps supply current, not very much. Recommended values here, 10K and 330 picofarads. But actually, if we look at these timing components, we'll see that we can change the frequency over a really wide range, right from 100 to 1 megahertz. So if we wanted a frequency of, say, 10K, we could use a 10 nanofarad capacitor with around a 10K resistor. I'm going to use a potentiometer instead of a fixed resistor, and that will allow me to vary the frequency, of course. What else is important here? Also important here really is this undervoltage lockout threshold. It's around 9 volts, which is a bit of a problem when we're using a 9-volt battery. So I'm actually relying that the voltage on the battery is slightly higher than 9 volts to begin with, which it probably will be. And also, this is probably around its more minimum threshold, I'm fingers crossed. So that's really it from the datasheet. Let's go and have a look at actually the drawing the circuit now. So here's all those components I popped into place. Let's zoom in. Okay, let's put the chip in the middle and let's line these MOSFETs up. So So that's going to be the low side MOSFET there. Actually, I'll move it down and I'll put the high side MOSFET here, aligned with high outs. We'll join those up immediately. That's the source of that MOSFET going to the drain of the lower side MOSFET. I'm going to put a VCC somewhere here. And I'm going to put our ground somewhere there. 2 grounds. Low out goes to that gate. You could use gate resistors, but I'm not going to bother for this little example. So if we remember the data sheet, that component there, the diode, goes the other way around. And it goes from VB from basically VCC. We need a capacitor now to do the other part of the bootstrap. Let's pop that here. And that goes from VS, which also goes to the VS, or the source of this high side MOSFET. There, like that. Okay, so that's the bootstrap bit done. We need the other side of the half bridge, and this is what the datasheet doesn't show, which, as I mentioned, I find incredibly weird. So we're going to connect that up. Okay, we're nearly finished already. Pretty quick circuit to make. Pull that over here a little bit. I'm just going to put my electrolytic capacitor here, rotate. So I just need my timing components adding. CT goes to ground, and we have that pin connected like that. And finally, we have this potentiometer. I'm going to draw it how I basically built it. And I'm actually drawing this circuit after I've made the actual circuit in the lab. And that's basically going straight from RT to the slider on the potentiometer, and then that side of the resistor to that pin there. That's a really silly thing to do, because if you think about it, if I turn the dial on the potentiometer all the way in one direction, then I actually get a short circuit here, and that sends this MOSFET driver crazy. So that's not a good thing to do, but anyway. So let's just set some values. I'm going to set this at 10 nanofarads, because if you remember the data sheet, it said 10 nanofarads and 10K, sets it to around 10 kilohertz. That's roughly what I want. That value there needs to be a little bit bigger. Make it 220 nanofarads. Of course, the data sheet tells you exactly what you'll need. These also could do with being a little bit bigger, 220 nanofarads each. They must be the same size. For reasons I'll explain in a moment. So I'm going to put 2 more things here. These are basically pads or outputs. and I'm going to label them X1, and X2. And then we're going to think about how this circuit actually works. Basically, that's where my transformer is going to join. Okay. So let's think how this works. So when we apply our VCC, in this case, it's going to be 9 volts. Forgetting all this part of the circuit, if you just look here for one moment, we've got 2 capacitors in series and they've got the same value. So we know that's going to divide the voltage by 2. So that'll divide a DC voltage by 2. So we know at that point, that node there, X2, we've got a constant 4.5 volts. Okay. So now if we look at these 2 MOSFETs, what happens is if Q1 switches off and Q2 switches on, the voltage here gets pulled down to ground. So there's 0 volts here. So if you think about it, this point now, X1, is 4.5 volts lower than X2. Then the MOSFET driver swaps the 2 MOSFETs around, so the Q1 switches on and this switches off. So the voltage here shoots up to the 9 volts. So now X1 is 4.5 volts higher than X2. And that's basically what gives us this square wave going between minus 4.5 and plus 4.5, which we feed to our transformer. So our transformer plugs into X1 and X2. R1, let's rename this RT, CT, sets our switching frequency. This just smooths out the DC. I've missed a wire. I can already see I haven't connected VCC. That needs to go there. What I've done there is a very silly thing as well, because basically this component has an internal Zener diode that clamps the voltage at 15 volts. Obviously, we're not using 15 volts, we're using 9, so we don't need anything additional there. But if I was to run this at, say, 20 volts, it would immediately break this MOSFET driver because it would draw too much current. It's clamped at 15 volts, so loads of current would flow. They can get away with that easily, or fix that easily, by adding a small resistor in between VCC and the voltage input. Other than that, that's exactly what we're going to build in the lab. Let me show you how easy it is to make a printed circuit board from that. I'm going to save that. Not advisable to do that, but now you'll see all my components basically appear here, and then if you look at the blue lines, shows you where the wires need to go. So it's really easy to wire it up like this. Can't get it wrong, although that looks disgusting. Obviously, that's not what we'd do if we were really making a PCB. So as I mentioned, I'm going to make a PCB later, so I'm not going to do this now. What I'm going to do is, I've already spoke for quite some time. I'm going to call it a day here. And in the next video, we're going to actually build the circuit. So just to summarize this video, we actually designed a simple switch mode power supply to drive a resonant transformer from a 9-volt battery. So as you saw the little clip at the start of this video, we can actually use that circuit to generate plasma. And that's going to be the focus of my next video. So in the next video, we're actually going into the lab. We're going to build that circuit we've drawn today, and then we're going to use it to generate some plasma. After that, we're going to talk about how we can actually make that voltage even higher. So I hope you found this video entertaining and enjoyable. If you do try it, please be careful. And thanks for watching. And please do like and subscribe because it really helps the channel. See you in the next one.